things you're going to become aware of as we go through this class is that we not only are interested in the data itself, but we're almost more interested in how the data varies from itself. Graphically, this shows up as the spread, and we're going to work today with that idea of the measures of spread. How do we numerically and quantifiably determine the measures of spread? So then, as a basic introduction to the idea of spread, we have three main calculations we can make. We can look at the range, that is the high to low values. It's not terribly useful. It doesn't give us a lot of information, so we don't spend a lot of time talking about the range. The most useful for us is the standard deviation. Standard deviation is a calculation you've probably made before, seen before. We'll be spending quite a bit of time with it this semester. Standard deviation is based on the mean. In its very calculation, we need the mean for this, as we'll see in a later video. However, this should give us a chance to pause, because we realize if we're using mean, we need to feel confident that mean is a good descriptor of the center of our data. Remember, for non-normally distributed data sets, we may not feel confident in mean. We might want to use median as our measure of center. Therefore, standard deviation follows that same pattern. The interquartile range, however, that's used when we want to discuss something that is a non-normally distributed data set. Here, the interquartile range, or IQR, is based on the median. We can always make the calculation of standard deviation or interquartile range, but when is it most useful? Well, it will be most useful when used with a data set that we feel confident with that as its center. Mean for standard deviation, and if I feel confident in my measurement of median for the center of this distribution, then interquartile range will be the measurement I choose to use. Let's make a connection here back to the ideas of our graphs. We're looking at a mound-shaped distribution, and here in A we may say that this is normally distributed, whereas in B we would say that it's heavy-tailed, where our graph, the tails are heavy, whereas C, it's light-tailed. It tapers off very quickly, it drops off, and the tails are almost non-existent. I'm going to take this opportunity to look at the equation for standard deviation. We're going to be working with this much more in the next video, actually making some calculations from sample data. But here we see the equation for standard deviation. Standard deviation is the square root of the sum of the differences that have been squared. X stands for each X value, each data point, having been subtracted by their mean values, that X bar value, and then those differences squared, and then summed up, all divided by n minus 1, is going to give us our sample standard deviation. Again, more on this later. In the next video, we're going to go in and we're going to actually calculate some standard deviations, and eventually I'm going to show you how this works on your calculator. When we have a non-normal data set, or a data set that's severely skewed or with extreme values, we may choose to use the interquartile range for our measurement of spread. Here you see a representation of essentially a timeline, a box plot, box and whisker plot. You see the 5-number summary here, the minimum value, the maximum value, Q1, the median value, and Q3. The interquartile range then is the distance between the Q1 and Q3 values. It'd be the box of the box and whisker plot. Therefore, the interquartile range is Q3 minus Q1.